Emmanuelle Crepeau. Let me introduce her first. So Emmanuelle is a specialist in control and inverse problem for PDEs. She has defended her PhD thesis at Paris-Saclay University under the supervision of Jean-Michel Coron and Lionel Rossier. She has been an assistant professor at the University of Versailles and also at Grenoble University. Since 2024, she is full professor at Université Polytechnique des Hauts-de-France, Valenciennes in France. She has contributed and participated in several research projects with colleagues from Chile, Brazil, and Colombia. So thank you very much, Emmanuelle, for accepting to give a talk in our seminar. So she will give a talk entitled Inverse Problem on Three-Shape Network. So as you want, Emmanuelle.
Thank you. So thank you very much for your kind introduction, Anna, and thank you also for the invitation. I'm very happy to be here with you today. So in this talk, I will present some recent and less recent results from for inverse problems. And first, I will introduce the networks we are interested in. So there are only finite shaped networks and especially tree networks. So tree networks are everywhere in nature or in engineering problems. We can think of, for example, to the arterial network or pipelines or irrigation canals. And for all those networks, there are a lot of mathematical problems. For example, you can want to regulate the height of water or detect problems in pipelines or determine blood pressure if you want with some non-invasive measurement, for example. So I give you some notations. So each edge of your network will be assimilated to a one-dimensional interval, okay? And the edges are called J. And we define the name of the branches by recurrence. In fact, you have the first branch, which is the root 1, and it's named, for example, 1. And these branches are 2 extremal nodes, okay? And so you have the root node and the extremal one, okay? Which we call L1, for example, it's because Lj is the length of your branch. And going off from this node, you have some children, okay? And so you define your network like that. You have to distinguish between internal and external nodes. So here, external nodes are, in fact, only the leaves of your network. So you distinguish between the root and the leaves, okay? And you have some internal nodes. And as we have, we are going to integrate on the network, I define the integral on all the network as the sum of the part of all integrals on all the edges. I also define a sort of bracket operator here, Fj. It's the balance between the fluxes. So you have the outgoing flux minus the sum of incoming one. Okay. So here I give you an example of a 9 branches tree network. So here you have the root here. So the first node is called 0, and it's with the length L1. Okay, so this root node here is L1 for this branch, but for these other branches here, you have 0, it's a new name, 0 here on L11. And so you have all the branches like that. Okay, so now we are ready to introduce our first inverse problem. So it's an inverse problem for a wave equation. So on each edge of your network, you have this wave equation here. So on each branch J, okay. So this wave equation with a potential Pj star, which depends only on the space variable. And you have a source term here, Fj, some initial condition at time 0. And you must have some boundary conditions. So you have boundary condition on external nodes. So first on the root node, you have some Dirichlet condition. And at the other external nodes, so at the leaves of your tree, you have also Dirichlet condition. And for the internal nodes, you have some transmission conditions. So you have the continuity of your solution. Okay, so here it's what comes from what we can call the mother branch, and it's equal to all the children. Okay, at the same node, here Lj for J is equal to 0 for the children. Okay. And you have some like Kirchhoff condition. Okay, so the flux coming from the mother is equal to the sum of the flux outcoming from the children. Okay. So our reverse problem is the following one. We have given data. So for each branch, you know the source term, Fj, the initial data, y0 and y1 for all branch. And you know also the boundary condition at the external nodes. But what you don't know is the potential on each branch. Okay, you don't know Pj star, never. So what you want to recover is this Pj star. So to do that, you need some additional measurement. The idea is to measure the flux of your solution at the leaves. Okay, so at the external nodes except the root, only on the leaves. And during a certain time, 0t. Okay. And the question we would like to answer are the classical one for inverse problems. So do the measurement of this flux uniquely determine the potential P star? Can we establish a stability, Lipschitz stability estimate? And finally, can we write an algorithm to be able to reconstruct the potential? Inverse problem for wave equation have been studied for decades. I am focused mainly on Kalman estimate to solve this inverse problem. So there are a lot of works. I didn't mention all of them. I'm not exhaustive at all for here, but you can look at the survey of Klibanov or Yamamoto to have some ideas of what have been done. For networks, there are less results for using Kalman estimates. In fact, most articles use a boundary control method. So there are a lot of works from Avdona, Belichev, and their co-authors. So with Lucie Baudouin and Julie Valin in 2011, we first studied the problem of uniqueness and stability result, not the algorithm, the first two questions for the inverse problem. And we proved this Lipschitz stability result. So if you measure your the flux of your solution during a time sufficiently large, so larger than time t0, if you have some regularity condition on your solution, and if your initial condition never vanish, then you have this Lipschitz result. So you have uniqueness and stability for your the recovering of your potential. So the proof of this result is mainly based on the Beckheim-Klibanov method. And to do that, we proved the two parameters Kerlman estimate. So to prove this Kerlman estimate, we designed a new Kerlman weight function. And to do that, we followed this article of Ben Abdallah, Dervenchian, and Le Rousseau. They established a Kerlman estimate for a 1D heat equation with a discontinuous coefficient. And the main idea they had was the following one. So we take the a usual polynomial weight function. It's usual for each wave equation, okay? And what do we ask? In fact, we only ask for the continuity of the weight function at the internal nodes. Okay, so for each internal node, we ask that the weight function coming from the mother is equal to the weight function for the children, okay, at the same internal node. We ask that this weight function is larger than 1. It's not very important, but what is very important to understand is that we don't ask for the Kirchhoff condition. If you ask for Kirchhoff condition for this potential, this weight function, sorry, in fact, you will ask some growth condition on the potential that will come when you will prove your Kerlman estimate, okay? And we don't want that. So instead of having a Kirchhoff condition, we ask for this hypothesis here. So we define this matrix here. So it's a matrix defined at all internal nodes. So you have one matrix for one each internal node. And it's a symmetric matrix. So here you have everything like that, okay? And what do we ask? We ask that this matrix has to be symmetric definite positive, okay, for all time between 0 and t. And you may need to find xj, beta, and mg such that you have those three conditions, okay? So with this matrix, in fact, you will manage to control when you will prove your Kerlman estimate, you will manage to control what will appear from internal nodes, in fact. That's the point. Okay. So with that in hand, we proved these two parameters Kalman estimate. So it's a 2 parameters Kalman because you have 2 parameters S and lambda. So here you have psi which is equal to exponential of S psi. So it's a 2-level exponential term here. Okay. And so this Kalman estimate is usual. So on the left-hand side, you have an energy term, okay? And on the right-hand side, you have your observation term here. Okay, so you have the observations of the flux of your solution at all external leaves known. Okay. So with these 2 parameters, we managed to prove the Lipschitz stability and the uniqueness result. So now the question is, can we write an algorithm to reconstruct the potential? So her first idea will be, okay, we minimize on the potential this difference here. So here you have what you measure. Okay, so Y star is the solution of the wave equation for your potential P star. So here it's what you have measured. And here it's the solution for potential P. Okay, and you minimize this functional over all potential. But if you do that, in fact, the problem is that this functional J is not convex. So it may have several local minima, and you are not sure at all that your algorithm will converge to your minimum. Okay, so you are not sure to find the P star. So our idea was to use the so-called Kalman-based reconstruction algorithm. So this algorithm is constructed such that it will converge without any guess of your potential. Okay, so it's something like we can call global convergence of the algorithm. And to do that, we will use Kalman estimates, okay, and not just Kalman estimate, but we will prove the global convergence of the algorithm thanks to the proof of the stability of due to Becker-Klebanov method. Okay, so we use all the proof of the Kalman to get the convergence of the algorithm. So this Seebeck algorithm was first wrote by Lucie Baudouin, Maya Debuan, and Sylvain Vedosa for a wave equation, for a problem on finding a potential for a wave equation, but on a bounded domain, not on a network. And later with Axel Hosses, they reconstruct the wave speed of a wave equation. And also Boulakia, Debuan, and Schwint applied this algorithm for retrieving a source term for a nonlinear heat equation. So our idea with okay. So in this first article in 2013, in fact, they used the classical 2 parameters Kalman estimate. Okay, but as I said before, when you have a 2 parameters Kalman estimate, you have a 2-level exponential in your Kalman estimate. Okay, so here, remember, here you have an exponential of an exponential. Okay, so when you apply some numerical analysis, it's a very big term, in fact. Okay, so it was a problem for them. So in 2017, they improved their algorithm, and to do that, they used a single parameter Kalman estimate. So of course, if you use a single parameter Kalman estimate, you will have a price to pay, and the price is that you will have a new term on the right-hand side of your Kalman estimate. And this new term is, for them, is like that. So you will have a new observation term, and you can get rid of. It's a problem because you don't want to observe this term. Okay, you don't want to measure this term. So to split this observation term, they use a cutoff function, eta, and the idea is that eta vanish on this observation set. Okay. So we tried with Lucie Baudouin, Julie Valin, Maya de Buan to do that, so to apply their C-break algorithm. And so the first problem was to prove a new Kalman estimate for the wave equation and networks, and Kalman estimate with only one parameter. So if you do that, the idea is to use the same type of weight function, okay? But you have some new condition here. Beta t must be larger than this quantity here. Oh, sorry. And so if you impose the continuity of your weight function at the internal node, now when you look at your matrix A, in fact, you cannot find xj, beta, and mj such that this matrix is always symmetric definite positive. It will be definite positive only for time less than tj. Okay, so between tj and t, you will have this remaining term here, which has a bad sign, and you cannot get rid of. Okay. So here is our new Kalman estimate with only one parameter. So here you have only one level of exponential here. And on the right-hand side of your Kalman estimate, you will have the usual part, which comes from the measurement of your flux on the leaves of your tree. But you will have also this new term in blue. And this new term is, in fact, it looks like the term that Lucie, Maya, and Sylvain get for their wave equation on Baudet domain. So it's a new term, new observation term. And here it's a little bit more complicated because here you have an observation on time and space. Okay, so O is a sum of all these, union of all these bounded domain here. And you will have also this integral here. And this integral, in fact, it's for all internal nodes. Okay, so you will have an integral in time for all the internal nodes here. Okay. And this is a problem here for us to have this term. So I have represented here for one branch. Okay, so you here I just look at one edge of your network. So here it's from edge 0 Lj, and so xj is the parameter coming from the weight function. It's non-positive, okay? And here you have this domain OJ, okay? So you have this domain on all the edges, plus of a new wave equation, and on the source term here, Fk is the difference between P star and Pk times the derivative in time of Y star. Of the initial condition, in fact, Vk at time 0, it's the derivative of Yk minus Y star at 0, but as I have the same initial condition, this one is equal to 0. And for the derivative in time of Vk at time 0, you have to use the fact that the derivative of Vk is the second derivative in time of this function. And as they solve the wave equation, you can find this value. It's P star minus Pk times 0, y 0. Okay, so what is very important for the Klein-Klebanov method is that P star will appear both in a source term and in the initial condition. And in fact, you have also continuity, Kirchhoff law, and homogeneous Dirichlet boundary condition at the external nodes. Okay, and so if you manage to prove that Vk, in fact, Vk is built with the unique minimizer of this functional. And this functional, what is it? It's the right-hand side of your Kalman estimate. So here, what I have to say is this quantity here, mu, it's known, in fact, because it's this quantity. So if Pk is known, you can construct the solution of your wave equation Yk, okay? And this star, it's your measure. Okay, so mu k is known for all time 0 t. And so if you can find this minimizer Vk, so if you minimize this functional, okay, then you can reconstruct P star, because in fact P star, if you know Vk, you just have to say, okay, P star is this quantity minus Pk divided by Y0, okay? So here you see that Y0 mustn't vanish, okay? That was our first hypothesis at the beginning of the story. Okay, so in fact, it means that in just one time you manage to find P star, okay? You take what you want as Pk and you have P star. But in fact, it is not true, because here, when you minimize this functional here, you have to know Fk. And in fact, if you look here, Fk depends on P star. And of course, you don't know P star, okay? So as we cannot minimize this functional here, because we don't know Fk, the idea is to replace, okay, we don't know Fk, so we forgot it, we replace it by 0, and we hope that, okay, we will be able to construct a sequence of potential that will converge to P star. That is the hope. And the second problem is what can we do with this blue term? So we will use a cutoff function, okay, eta phi. So we multiply, we'll replace Vk by eta phi times Vk, okay. And if we look at the equation satisfied by Vk, in fact, we will have a new source term Fk that will depend on eta, of course, on P star also. And for the initial condition, also we will have eta phi of 0 now. And we hope that we have continuity, Kirchhoff law, and the record boundary condition if we take a good eta. And okay, so here are what we will ask for eta. So you know that we will reconstruct P star thanks to this P star. Oh, sorry. P star thanks to this. I will not arrive. Thanks to this initial condition here. So the simplest idea is to take eta phi at 0 is equal to 1. Okay. We want that the blue term we want it to disappear. Okay. So we want that E of Vk is equal to 0. So what we ask for is that eta phi is equal to 0 on a big domain, bigger than this blue domain. And also, we will ask that eta vary in a small region in order to be manageable to calculate everything. And also, we want that Vk satisfies the continuity on Kirchhoff law at all internal nodes. So here I have represented two consecutive branches for our network, so a mother one and a children one. And you have your two domains where you want that eta is equal to 0. Okay, so everywhere eta here must be equal to 0. And here you want eta is equal to 1 at time 0. So you will ask that eta is equal to 1 just before this red curve here on this blue one here. So here eta is equal to 1 here, and 0 here and here. And so you will want that this eta varies slowly from 1 to 0 in this region. Okay, so it's possible because here, in fact, this small channel here is smaller than this one, in fact. That's the trick. And with this in hand, we managed to prove that this functional here is continuous, strictly convex and coercive, and so it has a unique minimizer on this set capital T. So we can apply this algorithm. So you take what you want as P0. Maybe you can take P0 is equal to 0, and you define recursively your pk like that. First, you calculate this mu k. So eta is known, d star is known, it's what you have measured, and you calculate the solution yk associated to pk, and so you have this mu k. Once you have that, you minimize your functional f with pk, which is known, 0 here, because you don't know the source term, so you take 0, and this mu k that you just calculate before, and you define a new intermediate potential p tilde k plus 1, like that. And it's an intermediate one because if it's too large, you get it, in fact. Okay. It's due to the Kalman estimate. P mustn't be too large. And And with the Beckham-Klimanov method, you manage to prove this stability result, in fact. So here, pk minus p star is the norm of the weighted norm of this difference is less than p0 minus p star times this quantity here. So if S is large enough, this will be smaller than 1, and you will converge to p star. Okay, so in the 3 minutes, I will show you some numerical examples. So first, for the simplest network, so only 3 branches. Just a remark here, the length of your network is 1.5. Okay, so if you imagine that so as the speed of your wave is equal to 1, the time needed for an information to go from this red node to this root node is 1.5. Okay. So here I have some simulations without noise. So on the first line, you have a historical reconstruction of your potential. So on each branch, okay, and here it's the same, but with only the end of the reconstruction. So the red curve is the exact potential, and the black line is the reconstruction. Okay. Here is the same problem, but with over potential. And what is important is that here, for example, because in the first simulation we took a potential that was equal to 0 at the internal nodes, but you don't need the continuity of the potential at the internal nodes. So here, the potential is equal to 0 at the internal node for the first branch, and is equal to 1 at the internal node for the second branch. So you don't need some continuity for the potential. Here is the same reconstruction, but with a different level of noise. So of course, if you have a lot of noise, it's much more difficult, especially to capture this step function. Okay. Here I give some numerical results for a wrong choice of parameters. In fact, in the reconstruction algorithm, we need that the time of observation is larger than t0. And t0, in fact, is given by the Kalman estimate, and it's larger than the length of the network. So I told you just before that the length was 1.5, and in fact, if you take 1.5, you manage to recover your potential, even if we don't have the result for this time. But if you take a time smaller than the length of your network, you don't manage to recover the potential at the root, because your information didn't have the time to go from the end of the network to the root. Okay. Here it's a much more complex network with 9 branches and only 6 observation leaves. And you can see that we managed to recover all the potential here. Okay, I think that's the end of, so I will just give a conclusion. So we managed with Lucy, Maya, and Julie to reconstruct the potential for the wave equation. And the question is, can we apply this method for other networks, maybe networks with loops, for example, or circles, and also for other equations, so for elasticity equations, for example. Okay, so thank you for your attention.
Thank you very much, Emmanuelle, for this very nice talk. Yeah. So let's ask the audience if there are any questions or comments. Please, I think you can use your microphones or also use the chat. So please.
I have one question. Yes.
Yeah, Johnny?
Okay. Yes. Thank you, Emmanuelle, for your interesting yes, talk. I have liked it. One question, if I have understood well, you in your trees, in your domains, you have considered the observation at the end of the branches, no?
Sorry, I have
The
considered.
observation domain is at the end of the branches, no?
Yes, exactly.
Is it possible, or does it make sense? Maybe not, but it doesn't make sense to consider observation domain in the interior of the branches. I don't know if it makes sense. Maybe not for your model.
To observe
In the
where?
part of the branch, inside the
Oh
branch.
yes, I didn't have the time to explain, but for the heat equation, we have two different results. One with observation on the leaves, and one with observation on part of the edges. Yes.
Yes, because I have
Internal
read.
observation or external observations. Yes. Yeah.
Yes. Thank you. And another short question. I have seen that you have talked about some cutoff functions that you had to build in order to. And the reason why you build those cutoff functions is because you have to deal with some blue term appearing in the functional at the end, and the functional that you wanted to minimize.
This one?
The reason why you have to build those cutoff functions is because you have to deal with the blue term appearing at the end of the functional.
Yes, this one, yeah.
That's the reason to build the appropriate cutoff functions.
In fact, if you don't build this cutoff function,
yes,
you will need some other observation terms. Because here you will have this quantity here, but you don't know the value of this quantity, in fact.
That's interesting.
The only thing we can do is to get rid of them, and so to multiply with a cutoff function.
Thank you. Interesting. Thank you very much.
Thank you.
Okay.
Yes.
Okay. We have one question in the chat from Luis Japu. He is asking for two parameters. Carliman, the method does not work.
In fact, if you take a two parameters Kalman estimate for the algorithm, it works. It was given by Lucie, Maya, and Sylvain in 2013 for the wave equation, not on network, but on a bounded domain. But in that case, in fact, they have to deal with very large terms, because here you have your to minimize this functional here, and so you have an exponential term of an exponential. So it becomes very large. So it was a numerical issue, in fact. Okay, so in fact, you can prove that you will converge, but numerically it's not so good.
Okay. Okay, thanks. Thanks. Other questions?
Yeah, I have one.
Yes, Eduardo, please.
Hi, everybody. Thank you, Emmanuelle, for your nice talk. Thank you very much. So, in your last slide, you mentioned, I cannot avoid the question about the KDV. Are you working on that, or do you think that is feasible?
No, I didn't work on that. Maybe we can do something because, in fact, Kalman estimate for KDV, it works. So yes, we can try.
Okay. Because with this approach, nothing has been done until today.
I don't think so. No.
Okay. Good.
But if you remember,
Okay.
it's not so easy to apply inverse problem for KDV.
No.
Yes.
Other questions? So I have just one question, mostly curiosity, I think. So is it important the size of the network for the results, or so we can obtain reconstruction for any size of the network, or the speed of conversion is somehow depends on the size?
In fact, what is very important when you have a large network, in fact, it should work, but when you look at the weight function here, in fact, XG, if you look at your XG, it doesn't appear here, but they are larger and larger. So in fact, you imagine you have X1, okay, it's non-positive, but X11 must be far from X1, much more far. So if you have a very, very big network, your XG will be larger and larger. So maybe it will be difficult, yes.
Okay. Okay, so thank you very much. I think we are a little bit out of time for more questions. And thank you very much. Yes, okay. Thank you.